Welcome to video 1 of your Chapter 17 AP Statistics lesson. Today we're going to talk about probability models. We're going to talk about specific types of random variables. Bernoulli Trials. The basis for the probability models we will examine in this chapter is the Bernoulli trial. We have a Bernoulli trial if there are two possible outcomes, success and failure. Now, those are just ways of labeling the outcomes. So, in other words, success is not necessarily a good thing. If the primary event we're interested in, say for a bunch of light bulbs being manufactured, is that counting the number of ones that are defective in a shipment of them, then success would be successfully defective. So all success means is has the characteristic we want. The probability of success P is constant, and the trials are independent. Those three things have to be true. A single Bernoulli trial is usually not all that interesting. A geometric probability model tells us that probability for a random variable that counts the number of Bernoulli trials until the first success. So if you're counting number of trials until first success and you've got a Bernoulli trial, you need to use the geometric probability model. Geometric models are completely specified by one parameter, P, the probability of success, and are denoted geom or maybe geometric, but just if you're writing it out, geom P. The geometric probability model for Bernoulli trials with parameter P is equal to the probability of success. Q is 1 minus P, that's the probability of failure. X is the number of trials until the first success occurs. So the probability that big X equals a specific X is equal to Q to the X minus 1 times P. Why? Because you've had X minus 1 failures and then boom, on the X trial you have a success. So remember, all the trials have to be independent, so you can just multiply those probabilities together. So it's failure, 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 on, and then success. The expected value of X, mu, is equal to 1 over P, and the standard deviation is equal to the square root of Q over P squared. One of the important requirements for Bernoulli trials is that the trials be independent. When we don't have an infinite population, the trials are not independent. But there is a rule that allows us to pretend we have independent trials as far as doing our calculations, because the differences in the probabilities are so small, it doesn't matter. That rule is the 10% condition. Bernoulli trials must be independent. If that assumption is violated, it is still okay to proceed as long as the sample is smaller than 10% of the population. The binomial model. A binomial model tells us the probability for a random variable that counts the number of successes in a fixed number of Bernoulli trials. So we're still talking about success, but we're not looking for the first success, and there is a fixed predetermined number of trials in this case. So that's how you tell the difference between binomial and geometric. Binomial counts successes and there's a fixed number of trials. Geometric, it's all open-ended as far as the number of trials. You just, the first success and you're done. And it's a probability that it takes that many trials to get the first success. Two parameters define the binomial model, which is why it's binomial, because it takes two parameters. So two, bi means two and nomial means name, so it takes two to name this model. N, the number of trials, and P, the probability of success. We denote this binom and then N, comma, P. In N trials, there are N choose K or equals, there's other ways you can talk about it, but N choose K is how we're going to go with it, equals N factorial over K factorial times N minus K factorial. Ways to have K successes. Okay, and so we're counting the number of combinations of K objects from N objects. And you read N choose K as N choose K. So make sure you remember N factorial means N times N minus 1 times N minus 2 times 3 times 2 times 1. And N factorial is read N factorial, not N. It's not an exclamation point, it's a factorial mark. Okay, so the binomial probability model ends the number of trials, P is the probability of success, Q once again is 1 minus P is the probability of failure. X, our capital X, our random variable, is the number of successes in n trials. So for the probability that big X equals a specific X is equal to n choose X times P to the X times Q to the n minus X. Again, we've got to count the number of ways to order our successes and failures, and that's what that binomial coefficient n choose X gives us. We have X successes, so our probability of success is multiplied by itself X times. Whatever n is, we have n minus X failures, so the probability of failure is raised to the n minus X power. Mu, the mean, the expected value, remember mu and E of X, same exact thing, is equal to n times P. Sigma is equal to the square root of n times P times Q. Normal model to the rescue. When dealing with a large number of trials in a binomial situation, making direct calculations of probabilities may become tedious or outright impossible. Fortunately, the normal model comes to the rescue. Actually, you have the calculator to help you, so it's really not that big a deal. But back in the day, it was huge that we could do the normal approximation. So as long as the success-failure condition holds, we can use the normal model to approximate binomial probabilities. The success-failure condition is that a binomial model is approximately normal if we expect at least 10 successes and 10 failures. So if n times P is greater than or equal to 10 and n times Q is greater than or equal to 10. When we use the normal model to approximate the binomial model, we are using a continuous random variable to approximate a discrete random variable. And so there's people who have philosophical issues with that. But it is an approximation and people recognize that. So when we use the normal model, we no longer calculate the probability that the random variable equals a particular value, but only that it lies between two values. Because remember, continuous random variables, probability has to do with area. In area, you have to have an area where there's some sort of width there. You have to have a range of values to find the area under whatever curve you're talking about. So what can go wrong? Be sure you have Bernoulli trials. You need 2 outcomes per trial, a constant probability of success, and independence. Remember that the 10% condition provides a reasonable substitute for independence. Don't confuse geometric and binomial models. Geometric, you're finding the probability that it takes so many trials to get your first success. Binomial, you have a fixed number of trials and you're counting how many successes you have. Don't use the normal approximation with a small sample size with a small n, and you will need at least 10 successes and 10 failures to use the normal approximation. Okay, so we've learned that Bernoulli trials show up in lots of places. Depending on the random variable of interest, we might be dealing with a geometric model, a binomial model, or a normal model. Geometric model when we're interested in the number of Bernoulli trials until the next success. Binomial model when we're interested in the number of successes in a certain number of Bernoulli trials, and normal model when we want to approximate a binomial model when we expect at least 10 successes and 10 failures. Okay, that's it for this video. We'll come back and do examples. I'll see you in just a minute.